Each generation believes it will leave an indelible legacy. But history tells a different story. From great cities of the past to lost technologies that no one can replicate, civilizations rise and fall. But what if future generations, cut off from simple energy sources, are left with nothing but the ruins of our machines? Could ours be the last to surpass the barriers of technological progress? Humanity, with over 8 billion individuals, has built a civilization that touches the edges of the atmosphere and reaches beyond. From satellites orbiting Earth to robotic rovers on distant planets, our technological prowess is unparalleled in the history of the solar system. These achievements are the result of a cascade of innovations, starting with the mastery of fire and culminating in space exploration, advances in robotics and artificial intelligence. The Industrial Revolution was a turning point that defined humanity's rapid technological ascent. Thanks to fossil fuels, coal, oil, and natural gas, this era unleashed a wave of progress. These energy-intensive resources allowed machines to replace manual labor, revolutionizing agriculture, transportation, and communication. As a result, the scale and complexity of human societies grew exponentially. However, this progress came at a steep cost. The resources that power our achievements are neither infinite nor abundant. Formed over millions of years from ancient organic material, fossil fuels are not just an energy source, but also the foundation for countless modern materials. Despite our accomplishments, this dependence exposes a critical vulnerability. What happens if these resources are no longer available? Can humanity recover after being deprived of the energy on which its world is built? To explore these questions, imagine a catastrophic event, an act of war, a nuclear holocaust, or a series of devastating natural disasters. In an instant, the complex systems that sustain our civilization could collapse. Power grids would fail, factories would shut down, and communication networks would disappear. Survivors would be left in an unfamiliar world, stripped not only of modern conveniences but also of the fundamental tools and knowledge that made them possible. This hypothetical doomsday forces humanity back to the Stone Age, literally, not metaphorically. Without functioning machines, libraries containing knowledge, or access to preserved infrastructure, survivors face the daunting challenge of rebuilding society from scratch. Unlike past civilizations that evolved gradually, these survivors will carry the knowledge of what was lost, but lack the means to recreate it. In the initial stages, survival would become the top priority. Food, clothing, and shelter, once trivial concerns, turn into the primary focus. Without farms and supply chains, survivors will resort to hunting, foraging, and crafting the simplest of tools. Wooden spears and stone knives will replace mass-produced goods. Clothing, if available, will be improvised from natural fibers or scraps. The absence of modern knowledge adds another layer of difficulty. Books that were once repositories of accumulated wisdom will likely be destroyed, leaving oral traditions and fragmented memories as the only guides. Even basic principles of metallurgy or medicine could be forgotten within a single generation, forcing people to relearn through trial and error. This scenario stands in stark contrast to historical collapses. When the Roman Empire fell, knowledge and infrastructure survived in fragments preserved by monks and neighboring cultures. Whereas in this imagined catastrophe, oblivion would be nearly complete. No internet archives, no encyclopedias, no functioning industrial machines. Only scattered remnants with little context for their use. The challenge for survivors is not just to endure, but to navigate a world devoid of the energy sources and raw materials that sustained the previous civilization. Fossil fuels, once readily accessible, would largely be depleted. Even if the knowledge of drilling for oil remained, the equipment needed for extraction and processing would no longer exist. This thought experiment is a sobering reflection on the fragility of modern civilization. Without its tools, infrastructure, and accumulated knowledge, humanity would face a struggle defined not by progress, but by the necessity of reclaiming the very basics of survival. The question remains, could we ever recover? And if so, at what cost? Let's continue our experiment. After a catastrophic collapse, survivors will find themselves surrounded by natural resources, but deprived of the knowledge and tools they once relied on. The first step in rebuilding civilization will be to return to the basics: wood, stone, and simple fibers like cotton and wool. These renewable materials will serve as the foundation for creating tools, clothing, and shelter. Initially, a thriving hunter-gatherer society could emerge. Basic tools such as axes, spears, and digging implements will allow survivors to collect resources more efficiently. With access to forests, wood becomes not only a building material, but also a crucial source of fuel for warmth and cooking. However, to progress beyond a subsistence lifestyle, survivors must transition from a rudimentary hunter-gatherer society to one capable of shaping its environment. This means moving from stone tools to metal ones, a leap that requires the discovery and mastery of metallurgy. The first important milestone is the creation of bronze, an alloy of copper and tin. Bronze can be produced at relatively low temperatures, achievable even with wood-burning fires. Copper melts at around 2010 degrees Fahrenheit, while tin melts at an even lower temperature of 445 degrees Fahrenheit. Combining these two elements yields a strong and versatile material, ideal for making tools, weapons, and primitive machines. However, transitioning to iron presents significant challenges. Although iron is abundant in the Earth's crust, its production requires a staggering temperature of 2,880 degrees Fahrenheit. A simple wood fire can't reach such temperatures. But charcoal, produced by burning wood in a low-oxygen environment, offers a feasible solution. Charcoal burns hotter than raw wood because it's essentially pure carbon. This process removes water, resin, and volatile organic compounds present in raw wood, which otherwise consume additional energy during combustion. Without these impurities, charcoal ignites more easily and releases energy more efficiently, generating higher temperatures. Additionally, its porous structure allows better airflow and heat concentration, and when paired with bellows to regulate air intake, it can generate the necessary heat to melt iron. However, this progress is constrained by the availability of sufficient wood. Metallurgy requires vast amounts of fuel, and as production scales up, the strain on forest resources becomes unsustainable. A society dependent on charcoal will quickly face a harsh dilemma: expand farmland to feed a growing population, or preserve forests to sustain metal production. This conflict highlights a critical bottleneck in the process of rebuilding civilization. Today, fossil fuels meet the immense energy demands of metallurgy. Without access to such energy sources, survivors would face the challenges of balancing the needs for food, materials, and energy, often having to prioritize one at the expense of the others. Our hypothetical future civilization, attempting to rebuild itself, will face a crucial and often overlooked obstacle: the lack of access to fossil fuels. Although these resources are the lifeblood of modern industrial society, they are finite and concentrated in deposits that are becoming increasingly difficult to access. In the event of a catastrophic collapse, the easily accessible reserves, the ones that fueled our early industrialization, will already have been depleted. Since the beginning of the Industrial Revolution, humanity has extracted approximately 750 billion metric tons of coal, oil, and natural gas. These readily available deposits were often located near the surface or in shallow geological formations. However, modern extraction methods now target increasingly deeper and harder to reach reserves. Some oil wells extend several miles below the surface, requiring advanced drilling technologies and vast energy investments, resources unavailable to a collapsed society. Even if a new civilization retains the knowledge of fossil fuel use, the tools and infrastructure needed to access them will be lost. Recreating these tools from scratch would require enormous amounts of energy and raw materials, creating a paradox. Accessing fossil fuels would first require fossil fuels to build the necessary technology. The absence of fossil fuels would pose severe challenges for any attempt to rebuild modern civilization. Fossil fuels have long served as an energy source and also as the foundation for many essential industrial processes and materials that underpin modern life. Replacing these resources will require not only innovative solutions, but also a fundamental rethinking of how materials are produced and utilized. Take steel, for example. This material is indispensable for construction, manufacturing, and countless tools. Producing steel requires high-temperature processing, over 2,730 degrees Fahrenheit, typically achieved using coal or natural gas. Without fossil fuels, such temperatures could only be achieved through alternative methods, such as biomass-derived charcoal, which, as mentioned earlier, places immense pressure on forest resources. Scaling up this approach to meet industrial demands would be nearly impossible without exhausting renewable wood supplies. Concrete poses a similar challenge. Producing cement, the binding agent in concrete, requires heating limestone and clay to temperatures exceeding 2,550 degrees Fahrenheit. Without fossil fuels, generating the necessary heat at production scales would require extremely resource-intensive alternatives, which would make concrete a cornerstone of modern infrastructure, scarce in a post-collapsed world. Plastics further illustrate this dependency on fossil fuels. These versatile materials derived from hydrocarbons are integral to medicine, transportation, and even renewable energy production. Lightweight, durable, and moldable, plastics are irreplaceable in diverse applications from sterile medical equipment to space exploration. Perhaps the most crucial component for any advanced civilization is ammonia, a compound essential to modern agriculture. Ammonia is used to produce synthetic fertilizers, which provide food for nearly half of the world's population. Industrial ammonia synthesis relies on methane, both as a key ingredient and as an energy source. Without access to methane, large-scale fertilizer production would vanish, threatening global food security and severely limiting agricultural output. The lack of fossil fuels will impact every aspect of rebuilding, from infrastructure to food production. Steel, concrete, plastic, and ammonia, materials we often take for granted, will become insurmountable challenges, requiring either costly innovations or significant sacrifices. These issues underscore the fragility of modern civilization and the steep climb future societies will face in reclaiming what was lost. Since we're talking about the challenges of rebuilding civilization, everything previously mentioned pales compared to the production of this key material of modernity. We're talking about silicon, not just as the second most abundant element in the Earth's crust, but as the foundation of modern civilization. Its unique property lies in its ability to act as a semiconductor, capable of controlling electrical current. This ability underpins every microchip, the essential component of almost all modern electronics, from computers to spacecraft. Historically, society lacked the means to utilize silicon beyond its natural forms, such as quartz or sand. The discovery of its semiconductor properties in the 20th century combined with breakthroughs in purification techniques, mark the dawn of the Silicon Age, a period characterized by an exponential leap in computing and technological capabilities. Semiconductors like silicon possess a unique band-gap energy, which allows for precise control of electrical signals. This property enabled engineers to create transistors, the fundamental building blocks of information processing, by layering silicon with other materials, such as phosphorus or boron. The result? Devices capable of performing billions of calculations per second. Without silicon-based microchips, our technological processes would have slowed dramatically. Picture a world where computational power is reduced to the rudimentary capabilities of vacuum tubes. This scenario would hinder progress across various fields, from medicine to astrophysics. Furthermore, space exploration, as we know it, would cease to exist, since autonomous spacecraft navigation, high-resolution imaging systems, and complex data processing all depend entirely on silicon-based technologies. However, there's a catch. The transformative power of silicon comes with a critical caveat. To function effectively in electronics, it must be purified to extreme levels, often exceeding 99.9999% purity. Achieving such purity requires temperatures of approximately 4,260 degrees Fahrenheit, far beyond the capabilities of traditional charcoal furnaces. This technological barrier was only overcome with the advent of specialized equipment capable of generating the necessary heat, such as electric arc furnaces. In space exploration, silicon is indispensable. It forms the basis of solar panels that power spacecraft, integrated circuits that process onboard data, and sensors that conduct detailed observations of distant celestial bodies. Without this material, the miniaturization of components essential for space travel would be impossible. Early space programs relied on bulky and unreliable electronics, which limited the duration and scale of missions. Silicon-based microchips revolutionized this paradigm, enabling the creation of compact, energy-efficient systems capable of withstanding the harsh conditions of space. If silicon were unavailable or its properties remained undiscovered, humanity's development trajectory would be vastly different. Our computing capabilities would regress to pre-digital levels, hindering innovations in artificial intelligence, telecommunications, and even climate modeling. The consequences would extend to healthcare, manufacturing, and many other aspects of society. Let's summarize. Humanity's ascent to its current technological peak has heavily relied on fossil fuels. Since the Industrial Revolution, approximately 715 billion tons have been consumed, with current annual consumption reaching 15 billion tons. However, remaining reserves are estimated at another 750 billion tons, and accessing them is becoming increasingly difficult. For example, the average drilling depth of oil wells has increased from 0.7 miles in the 1950s to 1.1 miles today, indicating a decline in easily accessible resources. A civilization with fossil fuels will face significant challenges. Fossil fuels are not only an energy source, but also a prerequisite for production of materials such as plastics and fertilizers, which are essential to technological progress. Without them, innovation would slow down, forcing society to rely on alternative materials and renewable energy sources. Potential solutions, such as producing methane from bio-waste, may offer a way forward, although scaling these technologies to a global level will be challenging. Progress is still possible, but at a slower pace, more deliberate pace, requiring significant adaptation in resource management and technological focus. History shows that, as the saying goes, necessity is the mother of invention, and while the path to a new civilization capable of reaching the stars will be much more difficult, it remains within the realm of possibility. the challenges posed by resource shortages and slowing technological development may drive creative breakthroughs, enabling humanity to adapt and thrive even in new conditions. After all, innovations born out of necessity can overcome limitations and forge a new destiny among the stars. Imagine a place where the boundaries of reality blur, where the very fabric of the universe is stretched, and the unknowable becomes known. This is not a science fiction world, but a reality created deep underground beneath the border between France and Switzerland. Here is the largest machine ever built by mankind, the Large Hadron Collider. It's a marvel not only of engineering but also of ambition, a testament to our quest to understand the universe at the most fundamental level. But could this device, designed to unlock the mysteries of particle physics, also be the key to opening portals to other dimensions? The idea of spatial portals may conjure up images of sci-fi gadgets and interstellar travel. Still, here at the European Organization for Nuclear Research, known as CERN, they represent the gateway to revolutionary discoveries. Here, the concepts of time, space, and reality are intertwined thanks to the high-speed collisions of subatomic particles. This is not just a story about complex mechanisms and theoretical physics. It's a journey into the heart of what makes our universe move, made with the planet's largest and most powerful particle gas pedal. As we go deeper, we learn how these experiments not only challenge our understanding of the universe, but change it. CERN is nestled in the beautiful landscapes of Europe, where the serene tranquility of nature meets human curiosity. The European Organization for Nuclear Research, the epitome of global cooperation, is home to scientists and engineers seeking to unravel the layers of our reality. CERN was founded in 1954 to unite nations in the pursuit of scientific knowledge, and has grown to become the world's largest particle physics laboratory. Here, more than 10,000 minds from over 100 countries converge to push the boundaries of human knowledge. The heart of the organization's research is located deep underground. The Large Hadron Collider, or LHC. This outstanding example of human ingenuity is 17 miles in circumference, and it's where some of the most advanced scientific experiments ever conceived are conducted. As the most powerful particle gas pedal on Earth, the LHC allows physicists to recreate the conditions that occurred moments after the Big Bang by accelerating particles to near light speeds and colliding them with each other. The LHC helps us explore the fundamental particles that are the building blocks of the universe. But CERN's role goes beyond particle physics. As a center of global scientific research, it's also a hotbed of technological advances. Innovations developed here, such as the World Wide Web, have fundamentally changed our world, illustrating how basic research by scientists has gone beyond the laboratory to impact society as a whole. This institution is more than a laboratory. Using the universal language of research and discovery, the European Organization for Nuclear Research brings people and countries together, demonstrating that our quest for knowledge knows no boundaries. If we delve deeper into the basic purpose of the Large Hadron Collider, we find that its true scientific excellence lies in the fact that it allows scientists to test and extend several fundamental theories of particle physics. This machine is as much about brute force as it is about precision and the subtle nuances of particle behavior at incredibly high energies. The standard model of particle physics, developed in the middle of the 20th century, describes the forces and particles that make up our universe. However, it's not complete. The LHC is a unique environment where particles collide at high enough energies to detect phenomena that can either confirm or refute this model. One of the key aspects of the research is the study of supersymmetry, the theory that every particle we know has a heavier superpartner. These partners, if they exist, could unlock many of the mysteries of the universe, including the nature of dark matter. The LHC also plays an important role in investigating the validity of string theory, a branch of theoretical physics that attempts to reconcile gravity with quantum mechanics. It suggests that point particles in particle physics can be replaced by one-dimensional strings. The vibrations of these strings appear to us as different particles. The energy levels achieved in this giant laboratory allow us to explore these ideas, potentially creating new particles predicted by string theory. But beyond the tangible, the LHC has entered the realm of what many consider science fiction. The idea of opening a portal is a term that's often misinterpreted by the sci-fi elements of popular culture. Scientifically speaking, a portal is not a mystical gateway to another dimension like in the movies or on television. Instead, it refers to the potential creation of microscopic black holes during particle collisions. These phenomena, predicted by the same string theory, would be extremely short-lived and would not pose a threat to our existence, as the sensational news of the yellow press suggests. While in pop culture, portals may be portrayed as doors to alternate realities or times, in the world of high-energy physics, they represent an opportunity to observe and study conditions and particles that can barely exist in the natural universe. These experiments have the potential to open up new dimensions of physics. Literally, by analyzing the particles produced by these collisions, scientists can gather evidence that either confirms these theories or sends them back to the drawing board. With its unprecedented ability to test these theories, the LHC acts like a giant microscope, magnifying the very fabric of the universe and helping us understand the fundamental principles that govern everything we see and everything we don't. Particle physics is constantly evolving, and each experiment and discovery pushes the boundaries of our understanding of the universe. From discovering fundamental particles to challenging the limits of physics, the achievements of this research center are monumental. At the center of such scientific advances is the discovery of the Higgs boson, a particle integral to the mechanism that gives mass to elementary particles. Discovered in 2012, this breakthrough confirmed a crucial part of the standard model of particle physics, and won the 2013 Nobel Prize in Physics. The existence of the Higgs boson, often called the God particle, has answered fundamental questions about how particles acquire mass. This discovery was a triumph of theoretical physics. Also of note is the recent public release of the discovery of the Higgs boson by the CMS collaboration, which marks a significant commitment to open science and collaborative research. Transparency fosters a global scientific dialogue in which hypotheses can be rigorously tested and new theories can emerge from shared knowledge. This release, which includes the unique combined software developed to search for the Higgs boson, allows scientists around the world to explore the intricate details of this monumental discovery. The resulting likelihood function with nearly 700 parameters captures the complexity of the experimental data, offering a multi-dimensional representation that defies even the most sophisticated visualizations. This openness not only democratizes access to cutting-edge science, but also enhances the collective ability to validate and build on key findings. But the journey didn't end there. CERN has played a key role in other significant discoveries, such as the isolation of antimatter and the detailed study of quark-gluon plasma, a state of matter thought to have existed just after the Big Bang. Another experiment called ALPHA has successfully trapped antihydrogen atoms, opening a new way to study the properties of antimatter. This pioneering work aims to answer the question of why the universe is made up mostly of matter, even though the Big Bang theory suggests that there's an equal amount of matter and antimatter. Another cornerstone of CERN's research is the study of quark-gluon plasmas using the LHCb experiment. By studying quark-gluon interactions, scientists are delving into the study of the strong force, the fundamental force that holds atomic nuclei together. Each discovery at CERN not only adds a new layer to our understanding of particle physics, but can also push the boundaries of what technology can achieve under such extreme conditions. These experiments require the precise coordination of hundreds of scientists and cutting-edge technology, reflecting the amazing collaboration of people around the world. As you may have realized by now, the LHC is not just a technology loop. It's a finely tuned experimental environment in which the most fundamental questions of physics are addressed. So, how does the Large Hadron Collider work? The process begins by feeding beams of protons into the collider with a chain of small gas pedals. Each proton begins its journey in a simple bottle of hydrogen, where electrons are stripped from it, leaving bare protons ready for acceleration. These protons pass through a series of gas pedals, gaining energy at each stage until they finally arrive at the LHC. Once in the collider, the proton beams are boosted to finite energy levels, reaching the 6.8 tera-electron-volt mark during the latest 2024 launches. This intense energy is necessary for the protons to collide with sufficient force to decay into a range of subatomic particles, some of which may never have been observed before. The whole process takes place on a scale that's difficult to comprehend with everyday analogies, but we'll still try to explain the concept fully. 1 tera-electron-volt is roughly equal to the kinetic energy of a flying mosquito. Thus, 6.8 TeV is akin to the total energy of about 6.8 flying mosquitoes. However, this energy is packed into a particle that is inconceivably smaller than a mosquito. The proton is a subatomic particle, meaning it's part of the nucleus of an atom, and has a diameter of about 1 femtometer. By comparison, a mosquito is about 1/4 inch long. So, to visualize this difference, if a proton were the size of a pea, a mosquito would be the size of a large skyscraper. But all the energy of a moving skyscraper would be packed into such a small object. So let's continue. Of crucial importance in the whole process is the achievement of proton beam stability, a state when the beams are dense and well-focused. The beams are carefully regulated or squeezed to ensure that they collide in the detectors at the points where they can be most effectively studied. This process involves precise control of the many magnets around the LHC ring that guide and focus the beams. The collider has already produced its first stable beams at unprecedented energy levels in 2024, marking the official start of this year's physics data collection season. The third year of LHC Run 3 promises 6 months of proton collisions with energies of 13.6 tera-electron-volts at even higher luminosities than before, meaning more collisions for data-gathering experiments. This phase will be followed by experiments with lead ions, providing a different set of conditions to study. Also this year, the ATLAS experiment has already achieved a milestone in particle physics by measuring the width of the W boson for the first time. This parameter, crucial for understanding the weak force carried by the W boson, was found to be 2,202 mega-electron-volt, which agrees well with the predictions of the Standard Model. Moreover, at the forefront of investigating the fundamental asymmetries of our universe, the LHCb collaboration has made significant progress in understanding the complex interplay between matter and antimatter. In recent experiments, they've studied the behavior of the neutral D mesons and neutral strange B mesons, uncovering new layers of complexity in how these particles violate charge parity symmetry. The neutral D meson, consisting of a charm quark and an up antiquark, has shown a peculiar quantum quirk. It can spontaneously transform into its antimatter counterpart and back again. This phenomena has been captured with unprecedented precision in recent data sets from the first 2 LHC runs. The current study aims to identify potential CP violations in these transformations, which may shed light on the predominance of matter over antimatter in our universe. Similarly, the neutral strange B meson, consisting of a bottom antiquark and a strange quark, showed time-dependent CP violations when decaying into charged kaons. This observation marks a significant advance, as it was achieved with statistical significance beyond the typical discovery threshold in particle physics. These results not only confirm the known behavior of these particles, but also open new avenues of research. With the LHC now operating at higher luminosity, future data could further refine these measurements, potentially leading to new physics beyond the Standard Model that could explain dark matter and matter-antimatter asymmetry. In the vast universe of information surrounding the Large Hadron Collider, many myths and sensational stories have taken root. Today we'll try to clear up these misconceptions and explore the real scientific picture going on deep beneath the surface. One common myth is that experiments at the collider can inadvertently produce black holes capable of consuming the Earth. While the LHC can create tiny black holes, they're on the quantum scale and evaporate almost instantly through a process known as Hawking radiation. Stephen Hawking's theoretical predictions convince us that these microscopic black holes pose no danger. They provide a fascinating insight into gravitational forces, but are far from the end-of-the-world scenarios depicted in science fiction. Another dramatic claim is that the collider opens portals to other dimensions, or causes catastrophic natural disasters. Such scenarios, although popular in movies and on television, are not supported by any scientific evidence. The LHC's primary mission is to test the predictions of theoretical physics, to study the particles and forces at work in the universe, not to disrupt the fabric of reality as we know it. CERN operates under strict safety protocols. Comprehensive checks and risk assessments are carried out regularly to ensure that all experiments are safe, not only for scientists, but also for the environment. Finally, stories of supernatural phenomena or secret experiments are completely unfounded. As a transparent scientific organization, its research is published and available to the global scientific community. The commitment to openness extends to public documentation, accessible databases, and collaborative projects across continents. As we continue our journey, we want to remind ourselves to remember to rely on proven facts and scientific research. As we delve into the theoretical underpinnings of multidimensional research at CERN, we are exploring concepts that push the boundaries of our understanding of the universe. This area of physics considers the possibility that our universe may not be limited to the 3 dimensions of space and 1 of time that we experience every day. The idea of higher dimensions comes from theories such as string theory and superstring theory, which suggests that particles are not zero-dimensional points, but rather one-dimensional strings vibrating in multi-dimensional space. These theories suggest the existence of up to 10 or 11 dimensions, which may help resolve inconsistencies between quantum mechanics and general relativity. In practice, researchers at CERN use the Hadron Collider to investigate these higher dimensions indirectly. One approach is to look for signs of particles that may exist only in these higher dimensions, or effects such as the formation of microscopic black holes. The search for extra dimensions is not just a quest for knowledge about the fabric of space. It also has practical implications for understanding the fundamental forces of nature, including gravity. If extra dimensions do exist, they may explain why gravity is much weaker than other fundamental forces. Beyond theoretical curiosity, the study of higher dimensions can lead to technological advances in fields such as quantum computing and materials science, as these concepts push the development of new technologies to detect and measure extremely small and fast phenomena. As we delve deeper into the uncharted frontiers of particle physics, a new CERN initiative, the Search for Hidden Particles Project, or SHIP, is poised to revolutionize our understanding of the cosmos. This ambitious project aims to detect elusive ghost particles that may hint at higher dimensions beyond our three-dimensional space. The SHIP experiment is based on an innovative concept. Unlike traditional collisions of the LHC, where particles smash into each other, SHIP will direct them toward a fixed target, increasing the probability of detection. The method is expected to be 1,000 times more sensitive than any existing equipment at CERN. These ghost particles, potentially constituting dark matter or other unknown aspects of dark energy, remain invisible under ordinary conditions because of their extremely weak interactions with ordinary matter. The implications of the discovery of such particles are profound and will probably change our fundamental theories of physics. Along with SHIP, plans are underway for a future circular collider, which should be a leap forward in particle collision technology. It's planned that this collider will reach its full potential by the middle of the 21st century and will push the boundaries of human technology and scientific research. Potential discoveries made at SHIP and the future circular collider could open new chapters in the history of our universe. From advancing our understanding of fundamental particles to creating new technologies, the implications go far beyond particle physics, giving a glimpse into the very fabric of the cosmos, and perhaps even into the higher dimensions that weave it together. As CERN continues to support its scientific achievements, the quest for knowledge is moving forward, promising a future in which the mysteries of the universe will be revealed one collision at a time. Imagine a civilization so advanced that it can build colossal structures around stars, capturing their energy and using it for unimaginable purposes. This is not the realm of science fiction. It's a concept proposed by one of the most brilliant minds of the 20th century. A visionary physicist, Freeman Dyson, envisioned a megastructure capable of enveloping a star, capturing its vast amounts of energy. This idea, while radical, is rooted in the basic principles of energy consumption and technological progress. But why would an advanced civilization need such a structure? As our civilization advances, our energy needs grow exponentially. But our most ambitious projects pale in comparison to the energy output of our sun, which releases more energy in 1 second than humanity has consumed in its entire history. Imagine harvesting every bit of a star's energy, turning it into a power plant with nearly limitless potential. If realized, this colossal undertaking would revolutionize how we think about energy and its possibilities. But what would such a structure look like? And even more intriguingly, how would we be able to detect it from our distant vantage point here on Earth? The problem lies in our ability to detect signs of such advanced engineering. While we are just beginning to tap into our planet's energy resources, discovering such an advanced civilization is exciting and frightening. Recent research has revealed unusual infrared signals from 7 distant stars, sparking debate and fueling imagination. Could these signals be techno-signatures? Either way, these anomalies defy natural explanations. What's behind these mysterious infrared glows? Are they evidence of advanced extraterrestrial engineering or natural phenomena that we've yet to understand? To understand the concept of Dyson spheres, we must first familiarize ourselves with the Kardashev scale, a method of measuring a civilization's level of technological development based on its energy consumption. In 1964, Soviet astrophysicist Nikolai Kardashev proposed this scale, dividing civilizations into 3 types, depending on their energy consumption. Type 1 civilizations use all the energy available on their home planet, including geothermal, solar, wind, and other natural energy sources. Imagine controlling the power of earthquakes and volcanoes to power our cities. This is the hallmark of a Type 1 civilization. Civilizations of the second type go even further, receiving energy directly from their star. This is where the Dyson spheres comes into play. By surrounding their star with massive structures, these civilizations can use almost all of its energy. Type 3 civilizations, in turn, are even more advanced and can harvest and harness the energy of their entire galaxy. They control the energy of billions of stars, making them unimaginably powerful. The relevance of the Kardashev scale to Dyson spheres lies in the connection between energy consumption and technological progress. As civilizations evolve, their energy needs grow exponentially, forcing them to develop ever more ambitious methods of meeting those needs. But how can we discover the Dyson sphere? One of the most significant milestones in cosmic observation, the development of infrared astronomy, can help us in this challenging endeavor. Infrared astronomy allows us to see the universe in a new light, literally. By observing the infrared spectrum, scientists can detect heat emitted by celestial objects and reveal details invisible to traditional telescopes. This capability has played a crucial role in the search for techno-signatures, signs of advanced civilizations beyond Earth. This journey began in the mid-20th century, when astronomers used infrared sensors to study space. These early works laid the groundwork for today's sophisticated infrared observatories, such as the Wide Field Infrared Survey Explorer, WISE, and the James Webb Space Telescope. These instruments have opened a new frontier in astronomy, allowing us to detect faint thermal signals from distant stars and galaxies. But what does this have to do with the search for Dyson spheres? Well, in the 60s, theoretical physicist Freeman Dyson proposed an audacious idea. An advanced civilization could build a massive structure around its star to capture its energy. He envisioned a swarm of solar or habitats orbiting the star and forming what we now call a Dyson sphere. But how could it possibly be detected if it blocked the light of its star? Of course, such a structure would emit vast amounts of infrared radiation, making it visible even from Earth. Dyson's hypothesis was more than just a thought experiment. It provided a viable way to search for intelligent extraterrestrial life. By surveying the excess infrared radiation around stars, we could find evidence for the existence of these colossal structures. The concept led scientists to the recent discovery of several stars with unusual infrared emission. Modern infrared astronomy opens new horizons in the search for Dyson spheres and other technosignatures. By observing the universe in the infrared wavelength range, we can detect thermal emission from celestial objects, allowing us to understand phenomena invisible to traditional optical telescopes. One of the most important instruments in this work is the Wide Field Infrared Survey Explorer. Launched in 2009, WISE has revolutionized our understanding of the infrared universe. Its mission is to map the entire sky in infrared light, revealing countless celestial objects, including stars, galaxies, and asteroids. This is a mosaic of the images covering the entire sky, as observed by the WISE, part of its all-sky data release. WISE's ability to detect excess infrared emission around stars plays an essential role in the search for Dyson spheres. By analyzing the heat signatures recorded by WISE, scientists can identify stars with unusual infrared emission, which may indicate the presence of advanced megastructures. One prominent example is the Hephaestus project, led by a team from Uppsala University. This ambitious initiative aims to identify potential candidate Dyson spheres by analyzing Gaia, 2MASS, and WISE data. Hephaestus uses a sophisticated system to sift through millions of stars in search of those with excess infrared emission that natural phenomena cannot easily explain. The project uses machine learning algorithms, including convolutional neural networks, to weed out false positives and identify the most promising candidates. The project's methodology is rigorous. It begins by collecting data from several sources, including precise measurements of the position and distance of the stars using Gaia, near-infrared 2MASS observations, and mid-infrared WISE data. This comprehensive dataset allows the team to create detailed models of potential Dyson spheres. The team then uses a grid search method to compare the observed data with theoretical models. This involves calculating the expected infrared emission for different configurations and temperatures of Dyson spheres, and then comparing these models to the observed infrared excess. Through this careful process, Hephaestus has identified 7 potential candidates for a Dyson sphere. All of these objects are M-dwarfs, stars known for their relatively low luminosity, making the detection of infrared excess even more intriguing. These findings are significant because they demonstrate the potential for using long-standing astronomical data for such detections. The quest to detect Dyson spheres and other technosigns is driven by ongoing advances in infrared astronomy. These innovations allow us to explore the universe with unprecedented precision and detail. One of the most significant breakthroughs in infrared astronomy is the development of adaptive optics and advanced sensors. Adaptive optics systems correct for distortions caused by the Earth's atmosphere, providing clearer and more detailed images of celestial objects. This technology is vital for isolating faint infrared signals from background noise. In addition, integrating machine learning algorithms into data analysis has revolutionized our ability to sift through vast amounts of astronomical data. These algorithms can identify subtle patterns and anomalies that may indicate the presence of technosignatures. Among the most revolutionary achievements is the James Webb Space Telescope, which has already managed to change our understanding of the cosmos in more ways than one. With its advanced infrared capabilities, the JWST allows us to look deeper into space and time than ever before. JWST's primary mirror, which is more than 16 times larger than the WISE mirror, combined with susceptible infrared instruments, can detect the faintest thermal signals from distant stars and galaxies. Essential is the telescope's ability to observe in the mid-infrared region of the spectrum. If they exist, Dyson spheres are likely to emit heat in this range, making them visible to JWST. By scanning the sky for these infrared signatures, JWST could provide compelling evidence for the existence of advanced extraterrestrial civilizations. However, its busy schedule, planned months in advance and filled with many other important research projects, limits the amount of time for searching for Dyson spheres. Radio astronomy, in addition to infrared observations, plays no small role in the search for technosigns. The Very Large Array in New Mexico is one of the world's premier radio observatories, capable of detecting radio waves across the universe. Radio waves can provide important information about the presence and nature of technosignatures. For example, a Dyson sphere may emit infrared radiation and radio signals as a byproduct of energy harvesting processes. VLA can detect these signals, offering a different but complementary perspective to infrared observations. Developing and implementing advanced technologies will only improve our ability to find technosignatures. However, the results of the team from the Uppsala University are not isolated. Another recent study entitled A Data-Driven Search for Mid-Infrared Excesses Among 5 Million Main Sequence FGK Stars by Gabriela Contardo and David W. Hogg found 53 stars with significant infrared excesses. This large-scale search also used Gaia, DR3, 2MASS, and WISE data to detect anomalies in the mid-infrared range. The technique involved training machine learning models to predict expected infrared magnitudes based on other stellar characteristics. Stars in some bands appeared significantly brighter than predicted, and thus were flagged as potential candidates. After applying additional filters to help avoid false positives, the study narrowed the 4.9 million sample to 53 stars. Analysis of these findings reveals several intriguing candidates. For example, one of the identified stars shows an infrared excess consistent with extreme debris disk characteristics, which could be mistaken for a technosignature. However, its older age calls into question existing models of planet formation, suggesting either an extended disk evolution or alternative processes. The implications of these discoveries are profound. If any of these infrared anomalies are indeed Dyson spheres, it would provide direct evidence of the existence of advanced extraterrestrial civilizations. However, the scientific community remains cautious. Natural phenomena such as dust clouds or the extreme debris disk can also provide similar infrared signatures. Therefore, each candidate requires careful follow-up observations to confirm or deny the presence of artificial structures. The controversy surrounding these findings emphasizes the difficulty distinguishing between natural and artificial sources of excess infrared radiation. Indeed, in general, the vast distances between Earth and potential candidates pose a severe problem. Many of the stars under study are thousands of light years away, making detecting and analyzing their infrared signatures extremely difficult. The farther away a star is, the fainter its signals are, and the harder it is to obtain good quality, accurate data. Some scientists argue that our current understanding of stellar and planetary dynamics is incomplete, and these anomalies may reveal new astrophysical phenomena rather than technosignatures. The search for extraterrestrial life has gripped humanity for centuries, evolving from philosophical speculation to a rigorous scientific approach. Today, scientists use various methods to detect signs of life beyond Earth, focusing on technosignatures and biosignatures. While technosignatures are indicators of advanced technological activity, including large-scale structures like Dyson spheres, unusual energy emissions, or artificial signals, biosignatures, on the other hand, are indicators of biological activity. They can range from detecting specific gases in a planet's atmosphere, such as oxygen and methane, to surface features indicative of life. Current and upcoming missions are crucial in detecting these subtle signs of life. For example, the James Webb Space Telescope can observe in the infrared, detecting the faint heat signatures of distant exoplanets and their atmospheres. This provides valuable data on potential conditions suitable for life. It has confirmed dozens of potentially habitable exoplanets in the past year alone. Another important initiative that goes shoulder to shoulder with JWST is TESS, the Transiting Exoplanet Survey Satellite, which aims to detect exoplanets by observing their transits through stars. TESS has already identified thousands of exoplanet candidates, many prime targets for further study with more powerful telescopes, such as Webb. Future missions promise to further enhance our ability to detect technosigns and biosigns. The proposed LUVOIR, Large UV Optical IR Surveyor, and HABEX, Habitable Exoplanet Observatory missions, are designed to directly image exoplanets and analyze their atmospheres. These next-generation telescopes will provide unprecedented clarity and sensitivity, allowing us to detect even the faintest sign of life or advanced technology. In addition to space observatories, ground-based telescopes, such as the Extremely Large Telescope and Square Kilometer Array, will play a crucial role. ELT, with its massive mirror, will be able to obtain direct images of exoplanets and study their atmospheres in detail. At the same time, SKA will focus on detecting radio signals from space that could indicate technological activity. The search for life is not limited to looking for existing civilizations. Scientists are also exploring the possibility of life in our solar system, focusing on moons such as Europa and Enceladus, which have subsurface oceans. Missions such as Europa Clipper and potential future missions to Enceladus aim to detect signs of microbial life in these hidden waters. As we continually refine our methods and technologies, each discovery, whether it confirms or disproves the existence of life, brings us closer to understanding our place in the universe. The journey is as important as the destination. It pushes the boundaries of science and ignites our collective imagination. And each innovation brings us closer to answering one of humanity's deepest questions. Are we alone in the universe? In the infinite depths of the universe lies a fundamental principle, as mysterious as it is omnipresent. This force governs the very fabric of existence, yet remains elusive to the casual observer. This is the story of entropy, a concept that reveals the hidden order in the apparent chaos of the cosmos. Here on Earth, entropy is evident in every rustling leaf, every rolling wave, and every moving cloud. It's the quiet organizer of natural processes, from the simplest to the most complex. But what is entropy really? It's a phenomenon often misunderstood as an ordinary disorder, but it's more than that. Entropy is a transformation, a movement from order to disorder, from concentration to dissipation. This is exactly why your coffee gets cold, why the ice melts, why the scent of flowers dissipates in the air. So let us understand how an order is hidden in what appears to be chaos, and how does this mysterious force shape our entire environment, from the smallest particle to the largest galaxy, and even the very course of life itself. There is a hidden force at work in every corner of our world, from the quiet forests to the bustling hearts of our cities. This force, often unnoticed, plays a key role in the great work of the universe. Imagine a dewdrop on a leaf. shimmering in the morning sunlight. As the sun rises, the dewdrop slowly disappears, and its particles disperse into the air. This phenomenon illustrates a fundamental principle of nature, the transition from a concentrated state, the dewdrop, to a dispersed state, the water vapor in the air. At the molecular level, this principle manifests itself as the tendency of particles to move from a state of concentration to a state of dispersion. This is similar to the way a crowd disperses after a concert, moving from a structured gathering to random scattered groups. In of our cities, this principle is reflected in the rhythm of daily life. The concentrated bustle of the morning rush hour gradually fades away as the day progresses. Entropy is often misunderstood as simple chaos or disorder, but it's much more nuanced than that. It's about transformation and change. Like a sandcastle slowly crumbling under the merciless waves, entropy is the inevitable transition from order to disorder. This concept is encapsulated in the second law of thermodynamics, a fundamental principle of physics. It states that in any closed system, entropy will either remain constant or increase over time. In other words, the natural course of the universe is toward greater dispersion and disorder. From the grand scale of the cosmos, where stars and galaxies form and disappear, to the minutiae of our daily lives. This principle is a universal constant. It governs the birth and death of stars, the flow of rivers, and even the fading heat in a coffee cup. Imagine a steaming cup of coffee left on a table. Over time, its heat dissipates into the surrounding air, cooling the coffee. This is entropy in action, redistributing energy from a concentrated state, hot coffee, to a more diffuse state, a cold room. Or take an ice cube melting on a warm day. The structured, solid form of ice turns into a puddle of water, whose molecules are free to move. This transition from a solid, ordered state to a fluid, disordered state is a classic example of increasing entropy. In every aspect of our universe, this quiet but relentless force is always present, subtly directing the flow of energy and matter. As we delve deeper into the theory, it's crucial to go back in time to the era when the concept first emerged. The history of entropy is intertwined with the minds of some of the most brilliant scientists in history. Our narrative begins with Sadi Carnot, a French physicist often referred to as the father of thermodynamics. In the early 19th century, Carnot was fascinated by the efficiency of steam engines, the driving force behind the Industrial Revolution. His research laid the foundation for the laws of thermodynamics, which were later incorporated into the concept of entropy. Carnot's visionary work described how heat engines work and focused on how energy is transferred and transformed. His theories have played a crucial role in understanding the dynamics of energy flow within systems. The next key figure in our story is Rudolf Clausius, a German physicist. Clausius was the one who introduced the term entropy in the mid-19th century. He built on Carnot's ideas by delving into the nature of heat and energy transfer. Clausius's work led to a more formal definition of entropy. He suggested that heat cannot spontaneously transfer from a colder body to a hotter one, the principle underlying the second law of thermodynamics. His mathematical formulation of this concept allowed it to be quantified, bringing clarity to its elusive nature. Another giant in this field was Ludwig Boltzmann, an Austrian physicist. Boltzmann's contributions in the late 19th century brought a statistical approach to thermodynamics. He linked the microscopic behavior of atoms and molecules to macroscopic properties of matter, such as temperature and entropy. Boltzmann's work was groundbreaking. He showed that entropy can be understood as a measure of disorder at the molecular level. His famous formula, S equals K log W, where S is entropy, K is Boltzmann's constant, and W is the number of microstates, gave a profound insight into the nature of this phenomenon. The legacy of these pioneering scientists is immense. Their collective work laid the foundation for modern thermodynamics and statistical mechanics, fields that continue to evolve and shape our understanding of the universe. Turning our gaze to the natural world, we find that entropy is at work in every ecosystem, shaping the environment and the life within it. Nature, in its infinite complexity, is a vivid canvas of disorder in action. Consider a fallen tree in the forest. Over time, it undergoes a remarkable transformation. Microorganisms, insects, and fungi break it down, returning nutrients to the soil. This process of decay and renewal is a manifestation of our principle, reflecting the cycle of life and death in nature. Rivers are also agents of entropy. They constantly change the landscape, cutting through rock and soil, and redistributing sediments from the mountains to the sea. This relentless movement and transformation of matter is a classic example of the role of this principle in geophysical processes. Weather is another area in which chaos plays a crucial role. Cloud formation, rainfall, snowmelt. These are all processes driven by the distribution and redistribution of energy in the atmosphere on a global scale. In the oceans, entropy is manifested in the life cycles of marine ecosystems. Coral reefs, for example, thrive on the delicate balance of nutrient cycles, temperature, and ocean currents governed by the principles of energy flow. Photosynthesis, the process by which plants convert sunlight into energy, is another interesting example. Here, the entropy principle plays a role in converting solar energy into chemical energy, a process fundamental to life on Earth. From the tiniest interactions of microscopic organisms to the grandeur of ecological systems, this fundamental force is the invisible conductor of the natural world. It is the underlying principle that nurtures the beauty and dynamism of our planet. Life on Earth, in all its diverse forms, is deeply intertwined with the principles of energy flow and transformation. This complex relationship between life and energy reveals a universe in which chaos and order coexist in a delicate balance. Consider the simple process of seed germination. This process is a microcosm of life's ability to use and organize energy. As the seed grows, it absorbs energy from the environment, converting it into structured, organized forms. However, there's a price to pay for this organization, an increase in the overall disorderliness of the system. In the human body, entropy is our constant companion. Our cells are energy conversion power plants, constantly converting nutrients into energy. This metabolic activity is vital to our existence, but it also leads to increased order as energy is released in the form of heat and waste products. Ecosystems are also valid examples. For example, in a rainforest, the flow of energy from the sun to plants and then through the food chain demonstrates the role of entropy in ecological processes. Each transfer of energy from one organism to another involves energy dissipation, contributing to the overall disorder of the ecosystem. Looking at the bigger picture, the evolution of life on Earth can be seen as a journey through entropy, from the first single-celled organisms to the complex network of life we see today. Evolution has been a process of increasing complexity, driven by the fundamental laws of energy and matter. In the grand narrative of life, entropy is not just a concept of decay or disorder. It's the driving force behind growth, complexity, and a constant cycle of transformation. Life in all its forms thrives in the delicate balance between order and chaos, a testament to the profound interplay of energy and matter. In the cosmic arena, the principles governing entropy show a universe in constant motion, a stage in which stars are born, live, and die in a great cycle of energy transformation. Star formation is a process of remarkable energy dynamics. Inside nebula, clouds of gas and dust collapse under gravity, heating up and eventually triggering nuclear fusion. It's a transition from potential energy to kinetic energy, a cosmic example of energy distribution on an enormous scale. The life cycle of stars can be seen as a narrative of energy transformation. In their final moments, massive stars explode as supernovae, dispersing their elements across the cosmos. This dispersion is a powerful demonstration of the universe's tendency to increase the dispersion of energy and matter. Black holes, in turn, represent one of the most intriguing aspects of cosmic entropy. These mysterious objects, which have such a strong gravitational pull that even light cannot escape them, play a significant role in the energy dynamics of the universe. The black hole event horizon marks the point of no return, where matter and energy are irreversibly absorbed, contributing to the overall disorder of the cosmos. By the way, our channel has already published a detailed video about the connection between black holes, Hawking radiation that depletes them, and entropy. We recommend you watch it. The expansion of the universe is itself a confirmation of these principles. Galaxies are diverging, energy is becoming more evenly distributed over vast space, and the fabric of the cosmos is stretching, all of which indicate that the universe is evolving toward a state of higher dispersion. The cosmic microwave background radiation, the afterglow of the Big Bang, provides a glimpse into the early universe. As we know, this radiation is a remnant of a time when the universe was hot, dense, and in a lower entropy state. Paradoxically, as the universe expanded and cooled, its randomness increased. And this is what led to the inevitable formation of the complex structures we see today. One of the most profound consequences of these cosmic processes is the concept of the heat death of the universe. In this scenario, the universe reaches a state of maximum entropy, where all energy is distributed so uniformly that further energy transformations become impossible. This is a future in which the universe is cold, dark, and devoid of the energetic dynamics that drive cosmic evolution. In this vast cosmic action, the flow and transformation of energy shapes not only the stars and galaxies, but also the very destiny of the universe. It is a continuous process of creation, transformation, and ultimately, disintegration. In the modern world, the concept of entropy has transcended its scientific origins, finding applications in a variety of fields, but subject to common misconceptions. Currently, entropy plays a crucial role in the development of advanced technologies. In the field of renewable energy, a thorough understanding of this concept is essential to improve the efficiency of solar panels, wind turbines, and energy storage systems. This knowledge greatly helps in optimizing the conversion of natural energy sources into usable energy. In the field of information theory, entropy has acquired a new meaning. It represents a measure of uncertainty or randomness in a system. This concept is crucial in data encryption and compression, where controlling and predicting information patterns is essential. Despite its scientific importance, entropy is often misinterpreted. A common misconception is to equate entropy solely with disorder or chaos. Meanwhile, while the definition that entropy leads to an increase in disorder is correct, it is worth clarifying that we're talking about the distribution of energy and the probability of certain states. Another misconception is the notion that entropy can be reversed or overcome. In popular culture, we see images of time reversal or spontaneous assembly of objects. However, according to the second law of thermodynamics, in a closed system, entropy can only increase or remain constant. Modern physics research is considering its impact on quantum mechanics, the behavior of black holes, and the ultimate fate of the universe. Beyond theoretical physics, entropy has practical applications in environmental science, engineering, and urban planning. It helps to model climate change, design sustainable systems, and understand urban development patterns. The future will undoubtedly bring new challenges and opportunities, and our understanding of this phenomenon will be critical in addressing them. Whether it is advancing technology, exploring space, or managing our planet and conserving its resources, entropy remains a fundamental concept that will continue to define our journey into the unknown. The deeper we look into the universe, the more mysteries it reveals to us. Gravity, the invisible force that binds the cosmos together, may not be as unchanging as we once thought. From ancient civilizations to Einstein's groundbreaking discoveries, our understanding of gravity has constantly evolved. However, recent discoveries suggest that there may be a cosmic glitch on the grandest of scales. A subtle deviation in the force governing galaxies and stars. Ancient scientists pondered the nature of gravity, laying the foundation for Newton's elegant laws. But it was Einstein in the early 20th century who changed our perception. His theory of general relativity describes gravity not as a force, but as a curvature of space-time itself. Despite its success in predicting phenomena such as black holes and gravitational waves, Einstein's theory has its limitations. When we turn our eyes to the scale of galaxy clusters and beyond, we encounter inconsistencies. Gravity seems to weaken slightly over billions of light years, and it's this phenomena that researchers now call a cosmic glitch. This anomaly may hint at new physics, perhaps an extension of the standard cosmological model to include a varying gravitational constant. Such a modification could reconcile these inconsistencies without reversing the established successes of general relativity. The discovery of a cosmic glitch is forcing us to rethink our understanding of gravity. Could this be the first clue in a new puzzle that will eventually lead us to a theory that unifies the fundamental forces of nature? Long before the scientific revolution, ancient civilizations had encountered the concept of gravity, although they understood it in very different ways. The Greeks, for example, believed in the geocentric model, in which the Earth was the center of the universe. Aristotle argued that objects fall in the direction of their natural place, and this theory dominated Western thought for centuries. In ancient India, Hindu scriptures describe the concept of gravity as an inherent force that pulls objects toward the Earth. Similarly, the Chinese philosopher Mozi in the 4th century BC suggested that objects fall because of the force of the Earth's energy. These early ideas, although primitive by modern standards, laid the foundation for future scientific research. It was not until the Renaissance that a more precise understanding emerged. The work of Copernicus, Galileo, and Kepler challenged Aristotelian views, paving the way for the pioneering work of Isaac Newton. Newton's formulation of the law of universal gravitation in the 17th century was a monumental leap. He described gravity as the force that attracts two bodies to each other proportional to their masses and inversely proportional to the square of the distance between them. This elegant equation united the heavens and the earth under a single universal law. In the early 20th century, Albert Einstein revolutionized our understanding of gravity. He proposed the general theory of relativity, which described gravity not as a force, but as a curvature of space-time caused by mass and energy. Einstein's equations suggested that massive objects such as stars and planets warp the fabric of space-time, creating what we perceive as gravity. This concept was visually confirmed during the 1919 solar eclipse expedition led by Sir Arthur Eddington. By observing the bending of starlight around the sun, Eddington provided one of the first experimental confirmations of the general theory of relativity. Consider this: almost a century ago, Einstein added fudge factor to his equations to bring them in line with the then accepted idea of a static universe, and later called this factor his greatest mistake. However, this very constant, lambda, reappeared many years later to explain the accelerating expansion of the universe. Einstein's theory also predicted phenomena such as black holes and gravitational waves that we have only begun to observe in recent years, further confirming the validity of his theory. The Event Horizon Telescope's image of a black hole in 2019 and LIGO's detection of gravitational waves in 2015 were monumental achievements in modern astrophysics. Despite its successes, however, general relativity has its limitations. It's inconsistent with quantum mechanics, the basis for understanding the subatomic world. This has led scientists to search for a more comprehensive theory that unites these two pillars of physics. In the quest to understand the universe, scientists have discovered anomalies that challenge our generally accepted understanding of gravity. These inconsistencies indicate that our current theories, while robust, may be incomplete. The general theory of relativity proposed by Albert Einstein has become a cornerstone of modern physics. The theory has been remarkably successful in explaining a wide range of phenomena, from the orbits of planets to the behavior of light around massive objects. However, recent research points to potential inconsistencies when the general theory of relativity is applied at cosmic scales. Recent research conducted by Robin Y. Wen and colleagues in 2024 hypothesized a cosmic glitch in gravity. Their research suggests that the gravitational constant may not be exactly constant over vast cosmic distances. In particular, gravity appears to be about 1% weaker when it comes to distances of billions of light years. This anomaly causes difficulties in our understanding of what's happening because it implies a deviation from Einstein's theory of extreme scales. To solve this problem, scientists propose a modification of the standard cosmological model, known as lambda, cold dark matter. This adaptation involves adding a new parameter that slightly corrects the gravitational constant on cosmic scales, without affecting its proven accuracy on smaller scales. The conflict between general relativity and quantum mechanics further complicates our understanding of gravity. General relativity best describes large-scale structures, such as galaxies and black holes, while quantum mechanics provides the best framework for understanding particles on the smallest scales. However, the two theories are fundamentally incompatible. One of the most striking proofs of this contradiction is the behavior of black holes. The general theory of relativity predicts the existence of singularities, points of infinite density at the centers of black holes. In contrast, quantum mechanics suggests that such infinities cannot exist, indicating the need for a new theory that could unify the two systems. Recent advances in technology, such as precise measurements of the cosmic microwave background by the Planck satellite, have provided new data that both confirm and refute existing theories. These observations have led to the discovery of the Hubble tension, a significant discrepancy between the observed and predicted expansion rate of the universe. The Hubble contradiction suggests that either our understanding of the early universe or the nature of dark matter and gravity needs revision. The cosmic glitch theory, which introduces a small change in the gravitational constant, offers one potential solution to this problem. In addition, the detection of gravitational waves by the LIGO and Virgo collaborations has opened new possibilities for testing gravitational theories. These observations provide an opportunity to observe the universe in a new way, potentially revealing deviations from the general theory of relativity that could not be detected before. The intersection of these anomalies with the predictions of quantum mechanics could lead to revolutionary discoveries. Experiments conducted at CERN at the Large Hadron Collider are aimed at exploring the boundaries between these two realms. searching for evidence that could bridge the gap between general relativity and quantum mechanics. In search of understanding of gravitation, some scientists suggest that it may not be a fundamental force, but rather an emergent phenomenon arising from deeper principles. This idea does not cross the traditional ideas about gravitation, but rather opens new ways of theoretical research. One well-known alternative is modified Newtonian dynamics, or MOND. Proposed by Mordecai Milgram in the early 1980s, the theory suggests that Newton's laws need adjustment at the very low accelerations, characteristic of the outskirts of galaxies. According to MOND, these changes can explain the observed rotation curves of galaxies without involving dark matter. MOND has had some success in predicting the behavior of stars and galaxies, where traditional theories of gravity fail. However, it is unable to explain phenomena on large cosmic scales, such as galaxy clusters and the cosmic microwave background, where dark matter remains a more acceptable explanation. Another interesting theory is emergent gravity, Eric Verlin proposed in 2010. Verlin suggests that gravity is not a fundamental interaction, but arises from thermodynamic principles of information storage on holographic screens. From this point of view, the universe can be described as a hologram, where gravity arises from changes in entropy associated with the information stored on these screens. To simplify, imagine the universe as a giant laboratory where books, information, are stored on shelves, holographic screens. The arrangement and number of books change over time, affecting the overall structure and creating what we think of as gravity. Verlin's emergent gravity has intriguing implications for our understanding of dark matter. Instead of invisible particles, the effects attributed to dark matter may be a consequence of emergent properties of space-time itself. This theory allows us to take a new look at the connection between gravitation and thermodynamics. In addition to Mond and Verlin's theory, there are several other alternative approaches. One such theory is modified gravity, or simply MOG, proposed by John Moffat, which introduces additional gravitational fields to explain the rotation curves of galaxies and the dynamics of galaxy clusters without dark matter. MOG suggests that these additional fields modify the strength of gravity on different scales. In addition, the concept of entropic gravity, closely related to Verlin's ideas, suggests that gravity arises from the tendencies of systems to increase entropy. This thermodynamic interpretation is consistent with the principles of statistical mechanics, providing a new lens through which gravitational interactions can be viewed. These alternative theories, although not universally recognized, open before us new perspectives and require further research and experiments. They force us to reconsider the view of gravitation not as an inherent force of nature, but as a consequence of deeper, fundamental principles. As we move toward the middle of the 21st century, our quest to understand gravity continues to push the boundaries of technology and knowledge. State-of-the-art experiments and missions are being designed to test the limits of our gravitational theories, yielding new insights and potentially revolutionary discoveries. One of the most significant ongoing projects is, of course, the acclaimed James Webb Space Telescope. JWST observations to date have been crucial for testing theories of gravity on the largest scales, especially those that predict deviations from general relativity. Another key player in gravitational research is the Large Hadron Collider at CERN. This particle gas pedal, the largest and most powerful in the world, collides protons at unprecedented energies. These collisions allow physicists to study fundamental particles and forces, including the potential discovery of particles that can mediate gravitational interaction at quantum scales. experiments at the LHC are critical to understanding how gravity can combine with other fundamental forces. Space missions such as the Laser Interferometer Space Antenna, LISA, also loom on the horizon. Planned for launch in the mid-2030s, LISA will consist of 3 spacecraft forming a giant triangular interferometer in space. This facility will detect gravitational waves with much greater sensitivity than existing ground-based detectors, such as LIGO and Virgo. The goal of LISA is to observe gravitational waves from the merger of supermassive black holes, which will test Einstein's general theory of relativity and provide new insights into dark matter and dark energy. But let's get closer to home, where Event Horizon Telescope continues to make groundbreaking contributions. In 2019, EHT obtained the first ever image of the black hole M87, demonstrating the power of synchronizing telescopes around the world to create a planet-sized interferometer. EHT is now focused on even more precise observations of black holes, including the one at the center of our galaxy, Sagittarius A. These observations will test the predictions of the general theory of relativity in extreme gravitational fields. In addition, let us recall the already mentioned recent study by Wen et al., which proposes a cosmic glitch in gravity, suggesting that the gravitational constant may vary over cosmic distances. This study will be further tested with data from the Planck satellite and future cosmic microwave background experiments. Upcoming missions such as the Simons Observatory and CMB-S4 aim to make more precise measurements of the CMB that can confirm or refute the existence of such a glitch, offering a deeper understanding of the nature of gravity at the largest scales. In addition, the Vera C. Rubin Observatory, which will soon become fully operational, will conduct the Legacy Survey of Space and Time. This survey will map billions of galaxies, providing a detailed view of the structure and evolution of the universe. The data from LLST will help test theories of dark matter, dark energy, and gravity, and possibly reveal new phenomena that will change our current understanding. Another exciting frontier is the search for quantum gravity using benchtop experiments. These experiments use highly sensitive equipment to detect tiny gravitational effects on very small scales, where quantum mechanical effects become significant. Such experiments are designed to bridge the gap between general relativity and quantum mechanics, which may lead to a unified theory of gravitation. These state-of-the-art experiments and missions represent the cutting edge of gravitational research. They are designed not only to test existing theories, but also to discover new phenomena that could revolutionize our understanding of the universe. Revising our understanding of gravity could have profound implications for cosmology, astrophysics, and technology. The anomalies and alternative theories that we've studied suggest that our understanding of gravity is far from complete. As our models improve, we can expect significant progress in several key areas. In cosmology, a more accurate model of gravity could solve existing mysteries, such as the nature of dark matter and dark energy. If gravity behaves differently over vast cosmic distances, it could provide a new explanation for the accelerated expansion of the universe and the distribution of galaxies. This could lead to a unified model of the cosmos that better integrates general relativity and quantum mechanics. For astrophysics, improved gravitational theories can improve our understanding of black holes, neutron stars, and other extreme environments. By accurately describing the behavior of matter under the influence of intense gravitational fields, we can better understand the life cycle of stars and the dynamics of galaxies. This knowledge may even reveal new types of astrophysical objects or phenomena. Technologically, advances in the understanding of gravity will undoubtedly spur innovations in various fields, For example, accurate measurements of gravitational waves can improve navigation systems and geophysical research. In addition, breakthroughs in quantum gravity could lead to new technologies based on quantum information and communication, revolutionizing computing and data transmission. Imagine a future in which our understanding of gravity will enable ultra-precise space-time sensors, leading to the development of autonomous vehicles, precision agriculture, and disaster prediction systems. As we wait for the launch of new missions, projects, and discoveries, the anticipation grows. Each step forward brings us closer to unlocking the mysteries of the universe, promising a future in which our understanding of gravity and the cosmos is richer and deeper than ever before.